Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali.
In the 1970s and 80s, I was a research computational mathematician who contributed new calculus and new algebra to the body of knowledge of modern mathematics. As an aside, on weekdays, I did my stability investigations full-time and alone. I conducted my mathematical research in the early 1980s and in College Park, Maryland, United States. Tennis was the diversion that took me off the mathematician's blackboard and took me away from the stress of inventing new calculus. On weekdays of the early 1980s, I spent the last 3 daylight hours at the tennis courts that were either in College Park, Maryland, or at the Rosemary Hills, Littensville local park that was near my home of apartment 303 of 1915 East-West Highway, Silver Spring, Maryland. In the early 1980s, I spent my weekends in Baltimore, Maryland. The city of Baltimore describes itself as the birthplace of the U.S. national anthem, the Star-Spangled Banner. In Baltimore, I was a late afternoon regular at the Druid Hill Park tennis courts and at Clifton Park tennis courts. A recurring conversation with my older tennis partners was that during the 1950s segregation era, that Druid Hill Park tennis courts displayed whites-only signs. As a black African-born research mathematician, my presence within the American research mathematics community was very isolating. American science is grounded on a legacy of institutional racial discrimination. There is far more segregation and separation in American science than in American sports. That American legacy of institutional segregation and separation is the reason I was the only person to ever win the top prize in the field of supercomputing and to win that prize alone. In contrast, that prize is won only by a team of up to 50 supercomputer scientists that were armed with a supercomputer that cost up to $1.25 billion. My research in extreme-scaled computational algebra included my theoretical efforts to determine a priori the condition for the stability of the partial difference equations of algebra that I invented as approximations for the 9 partial differential equations of calculus that I also invented. That is, I investigated the error propagation and growth of my partial difference approximations, and I did so by simplifying the governing partial differential equations and by simplifying them to the heat equation or wave equation that is each linearized and that are described in standard references on the partial differential equations of calculus. For my finite difference discretization of the first order hyperbolic partial differential equation, my amplification factor was a complex number, and the stability condition for such first order hyperbolic partial differential equation is that the modulus of the amplification factor is equal to or less than 1. The eureka moment of my life occurred at 8:15 in the morning of the 4th of July 1989 in Los Alamos, New Mexico, United States. That was the moment I discovered practical parallel processing and became the first person to understand it as the vital technology that will underpin every supercomputer. My discovery represented a major shift from the sequential processing supercomputer of the 1980s and earlier that computed with only one processor to the modern supercomputer that computes with up to 10 million processors. Practical parallel processing that I discovered for supercomputing changed the ways scientists, engineers, and researchers solved their toughest problems. The reason I remember that 4th of July 1989 so well was that it was the Independence Day of the United States. Because I realized that I was making history, I worked every day, including the Christmas days of the 1980s. Back in the 1980s, the supercomputer scientists in my small circle did not understand what I was working on and steadfastly declined my invitation to collaborate with me. It's normal for 50 multidisciplinary supercomputer scientists to have collaborated with me and do so to make my parallel processed supercomputer calculations completed a few years earlier. In contrast, I was able to solve the grand challenge problem of supercomputing and solve it alone. The reason I could solve it alone was that I had more scientific knowledge than each member of that 50-person team had. The knowledge that I acquired over 16 years of supercomputing was the reason a grand challenge problem that is impossible for 50 scientists to solve as a team of researchers is in fact possible for me to solve alone. Because I knew more about the parallel supercomputer than they did, I had a sense of urgency and the surreal feeling that I was making an invention that was bigger than myself. For the 16 years onward of June 20, 1974, I kept moving forward towards the jagged frontiers of the parallel supercomputer. I moved forward even as vector processing supercomputer scientists mocked me and made fun of my belief that parallel processing will overtake vector processing as the technology that powers every supercomputer. I moved forward with my invention in progress because I knew that my discovery of practical parallel processing would put the name Philip Emeagwali into books on the history of science. My sense of urgency that history was in the making was why I spent 16 years working alone and unpaid, and doing so to invent practical parallel processing as the technology that makes every supercomputer super. As a research mathematician of the 1970s and 80s, my quest was for new algebra, new calculus, and new mathematical knowledge that was newsworthy and that was not in any mathematics textbook. The new mathematical knowledge that I contributed to mathematics that then US President Bill Clinton mentioned in his White House speech of August 26, 2000 was the Philip Emeagwali formula that I used to figure out how to divide the toughest mathematical problems into a million smaller problems and how to then solve those smaller problems across a million processors. I visualized my processors as tightly encircling a globe and encircling it as a new internet and encircling it in the manner the internet circumscribed planet Earth. The most productive decade in my research for new computational mathematics was the 1980s. In 1981, I was an extreme-scaled computational research mathematician in College Park, Maryland, United States. College Park is a small town of 30,000 residents in Prince George's County. College Park is to American mathematicians what Abuja is to Nigerian politicians. In College Park, Maryland, I identified myself as a research computational extreme-scaled mathematician that was at the intersection of numerical analysis and the partial differential equation. Those two fields of study are at the crossroad where physics, applied mathematics, and computer science met. Those two fields of study are particularly useful to physics, engineering, and medicine. Each afternoon and at the blackboard in the mathematics coffee room in College Park, I might scribble a system of partial differential equations of calculus that is impossible to solve directly, as well as its companion system of partial difference equations of algebra that I hoped to solve across my new internet that is a new global network of commodity off-the-shelf processors. Once again, it's impossible for any mathematician to exactly solve an initial boundary value problem of calculus that is governed by the 9 partial differential equations that I invented and that are my contributions to calculus. My solution strategy was to move away from my blackboard and to do so by paradigm shifting to a new internet that is a new global network of 64 binary thousand processors that were identical to each other, that were tightly coupled to each other, and that shared nothing between each other. Each of my 65,536 processors operated its own operating system. College Park is 4 miles from the northeast border of Washington, District of Columbia. In 1981, I was living at 1915 East-West Highway, Silver Spring, Maryland, rather than in College Park, Maryland. I lived in Silver Spring, in part because it was midway between the city of College Park and the Foggy Bottom and Adams Morgan neighborhoods of Washington, District of Columbia, and the National Institute of Health, Bethesda, Maryland. Those were my favorite places. In the early 1980s, my wife Dale was conducting her own research in the field of molecular biology. On my typical weekdays of the early 1980s, I arrived at 8 o'clock in the morning at my desk in the Graymax building at 8060 13th Street, Silver Spring, Maryland, United States. In the 1980s, the Graymax building housed the United States National Weather Service. The Graymax building has been reconfigured as an apartment building. At 12 noon and on weekdays, I will take a shuttle bus for the 25-minute ride from Silver Spring Metro Station to College Park, Maryland. In College Park, I spent a lot of time in the coffee room, for research mathematicians that was at 4176 Campus Drive, or inside the nearby research library that had specialized collections of mathematics, physics, and computer science. Or I might be attending a research seminar on new mathematics that is given by a research mathematician that is visiting from a different country. What was a day like in my life as a research mathematician of the early 1980s? At 3:30 in the afternoon, I walked over to the main lobby of 4150 Campus Drive to socialize with research physicists and astronomers, spending about 30 minutes conversing over tea and cookies. At 4 o'clock in the afternoon, I carried my heavy tennis bag to the nearby 14 tennis courts at Fieldhouse Drive, College Park. As a research supercomputer scientist, I was invincible throughout the decades of the 1970s and 80s. What was it like? What was a day like at the frontier of mathematical and scientific knowledge? About twice a week, and in the decade of the 1980s, I attended research seminars in Laramie, Wyoming, Baltimore, Maryland, Twin Cities, Minnesota, and Washington, District of Columbia. Each research seminar was a show and tell presentation on what the researcher discovered and on his current and future research projects. After I had attended 1,000 research seminars, I learned how to conduct an extreme-scaled scientific research and do so at the jagged frontiers of knowledge in mathematics, physics, and computer science. Those scientific seminars sharpened my intuition, which in turn made it possible for me to conduct research alone and to solve the grand challenge problem of supercomputing. The top prize in the field of supercomputing is normally won by a team of up to 50 supercomputer scientists. In 1989, I got the attention of the supercomputer industry when I won the top prize in supercomputing and won it alone as a 35-year-old. My contribution to the development of the parallel supercomputer was possible because I was one of the few people in the world that religiously attended 1,000 scientific seminars at the frontier of human knowledge. Without those 16 years of research that I conducted onward of June 20, 1974, and at the supercomputer that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States, giving me the top prize in the field of supercomputing would have been akin to giving the Oscar Award for lifetime achievement and giving that recognition to a child star. In the early 1960s, the system of partial differential equation that governed the petroleum reservoir was crude. The equation is called the Laplace equation. When applied to a heterogeneous real-world porous medium, the Laplace equation had variable coefficients and was ironically simulating an unsteady state porous medium fluid flow problem, but simulating it as a steady state fluid flow problem. In the early 1960s, Fortran was not yet widely available. For that reason, the early petroleum reservoir simulation codes were written in a less user-friendly assembly language. The assembly language is notoriously difficult and is the only language the computer speaks directly. The assembly language is still used in supercomputing programming contests and used because It allows direct hardware manipulation, as well as allowing access to specialized processor instructions. Back in 1961, petroleum reservoirs were simulated at about 20,000 floating point arithmetical operations per second. The more geologists know about the flow of crude oil and natural gas that is flowing deep inside a petroleum reservoir, the more that reservoir engineer knows where to drill an oil well. Knowing the best places to drill oil wells means that more crude oil and natural gas can be recovered. A state-of-the-art subsurface reservoir simulation is a parallel processed extreme-scaled supercomputer model of the motions of crude oil, injected water, and natural gas that is flowing across a porous medium that is often 1 mile deep and the size of a town. The parallel supercomputer that enables a trillion-celled petroleum reservoir simulation is the modern divining rod that enables the petroleum geologist to simulate an oil field and to do so in its entirety and to do so with the utmost resolution. The parallel supercomputer is used to understand the connectivity between petroleum reservoirs and used to solve all those seemingly impossible to solve grand challenge problems, and used to compute their initial boundary value mathematical problems, and used to unravel the mysteries that were buried 1 mile deep inside an oil field. Searching for the elusive, massively parallel processed solution to the toughest problem arising in abstract calculus and arising in extreme scale computational physics was like searching for a black goat at midnight. My scientific journey to the farthest frontier of technological knowledge and my quest for the fastest supercomputer that is a new internet was a mathematical journey from fiction to fact to forecast. The fastest supercomputer is where humanity's future will take place. Thank you.
Insightful and brilliant lecture.